Hello students, today topic is design of tubular heat exchanger. So before starting this topic, I'd like to make you familiar with two more topic that is basically not a part of your syllabus, but it is important to learn. Why it is important to learn? Because you can see here, will it work? It's not working. Okay, fine. So design of tubular heat exchangers. So far we have studied about many type of heat exchangers, and out of them one was the tubular heat exchanger. So when it involves some calculations, and on the basis of those calculations we design the tubular heat exchangers. So before calculating or before you can say starting the calculation part, we have to assume something for this designer tubular heat exchangers. Number one assumption is that heat transfer is under steady state conditions. So whenever we design a tubular heat exchangers, then we assume that the heat transfer will be under steady state conditions. First assumption. Second says the overall heat transfer coefficient is constant throughout the length of the pipe. Third is there is no axial conduction of heat in the metal pipe. Fourth is the heat exchanger is well insulated and the heat exchange is between the two liquid stream flowing in the heat exchanger, and there is a negligible heat loss to the surrounding. So here in this slide you may be seeing that there are the two new terms. One is the steady state condition and second is the overall heat transfer coefficient. So they must be taught. Actually the steady state conditions we have already learned. So first I'll talk about the steady state conditions and then I'll talk about this overall heat transfer coefficient. So steady state conditions. So far we have covered some example like the conductive heat transfer through rectangular tube, tubular pipe. All were the example of steady state heat transfer conditions. So simply you can say that this is the outside region and this is the inside region and it is a wall. So you can see here there is a temperature 20 degree and here the temperature 6 degree exit. So this temperature is varying with the location. At this location it is 18 degree, then 16, 14, 12, 10, 8 and finally 6. So temperature is changing with the location but it will not change with the time. Mean to say that if it is 18 here at time 1 p.m. then at time 2 p.m. It will be 18 only. Okay, that type of the heat transfer is known as steady state transfer of the heat transfer. So steady state condition imply that time has no influence on the temperature distribution within an object, although temperature may be different at different location within the object. Contrary, if we talk about the unsteady state heat conditions, the temperature may change with location and times. So for example, it is 12 here at a time 10 a.m. Then at the time 2 a.m. it may be 14 or it may be 10. So if these fluctuations takes place, and this is a real thing that it happens so practically, but theoretically we assume that is a steady state heat transfer. If we consider this fluctuation, then calculations are very tedious. So to simplify and just for an approximations, we can assume that there is a steady state heat transfer conditions that we have assumed our the first condition for the design of tubular heat exchanger. Second is the overall heat transfer coefficient is constant and throughout the length of the pipe. Now I'm coming, what is this overall heat transfer coefficient? See, here are the two circular discs. One is this lighter patch, one is the bit darker patch. Okay, so it is basically a cross section of the pipe. There is a pipe and it is having this much thickness. This dark zone is indicating the thickness, and here is the temperature, and here there are the two temperature has been shown, Ti and T infinity. Fine. and a temperature T1 exists here and a temperature T2 exists here. So if we calculate the heat transfer through the tubular pipe, so let the liquid is flowing through it and we wish to calculate that how much heat will be lost, then you can say that first of all this heat will be transferred from this inside surface of the pipe to the inner material. Fine. So it will be a, this is metal and this is fluid. So this heat transfer will be your convection. So first of all there will be convection. Then there will be a heat transfer to the body of this pipe, and it is a metal, and that's why this heat transfer will be termed as conduction. Finally, the body or the pipe surface will get heated up and it will emit the energy to the surrounding, and that loss of the energy will be via convections. So to describe the whole process, you can see here, this is the temperature and this is the distance. So this is Ti is the inside the pipe metal surface T1 and T2, and this is the outside temperatures. So we can write this basic equations that Q is equal to Ti minus T infinity divided by thermal resistance. The concept of thermal resistance I have explained you in the earlier cases. Here also I can explain. It is the relationship which set the analogy, or you can say the same, you can say it is what I'll say. This is similar to Ohm's law, in which we used to say that V is equal to IR. V is the your, what to say, V is the potential difference and I is the current and R is the resistance. So here in this case Q is the rate of the heat transfer. This Ti minus T naught T infinity is the your what to say, this is the drying force, and RT is the thermal resistance. So this total thermal resistance RT will be equal to RT inside convection, RT conduction, and RT outside convection. If we will sum these three, then for RT inside convection it will be 1 upon HI. For this tubular pipe we have learnt that the value of RT conduction is natural logarithm Rho upon Ri divided by 2 pi Lk plus 1 upon H naught A naught. This is the RT value for convections that is taking place outside the pipe. So these equations can also be written as Q is equal to Ui Ai Ti minus T infinity. So Q is the amount of heat transfer and Ai is the area and Ti minus T infinity is the temperature difference, and Ui is the value that we generally use to write here. We have learnt that the rate of convective heat transfer can be given by Q is equal to HA Ti minus T infinity. So that H has been replaced by a overall heat transfer coefficient. This overall heat transfer coefficient indicate the sum of the convection and conductions. So for convenient, we can write here Q is equal to Ui Ai Ti minus T infinity. So from here we can write Q is equal to Ti minus T infinity divided by 1 upon Ui Ai. If you will, you can write this Ui Ai in this form also. So in a way this 1 upon Ui Ai is symbolic or similar to the RT value, because here from this equation if we compare these two equations, so the value of RT is equal to 1 upon Ui Ai. So 1 upon Ui Ai will also equal to this value that has been shown here, 1 upon Hi Ai plus natural logarithm of Rho by Ri divided by 2 pi Lk plus 1 upon Ha H naught A naught. So this is the case when we are considering the inside area of the pipe. Fine. This overall heat transfer coefficient is based on the inside surface area of the pipe, and it will be Q is equal to U naught A naught Ti minus T infinity if we calculate the overall heat transfer coefficient based on the outside surface of the pipe. And in both cases the value of this equation and this equation will be similar. So from this whole story what you have to learn that Q is equal to Ui Ai Ti minus T infinity, and this Ui is the overall heat transfer coefficient. Okay, this I will explain, or we will use in the, mean to say that let there is a pipe, and that pipe has different thickness. So if the thickness is different, then this UI will be different. But when we design the tubular heat exchanger, then we say that the coefficient is constant throughout the length of the pipe. We assume like that there is no fault in the manufacturing of the pipe. It is uniform in thickness and same material has been used throughout the length. Fine. So to understand the design of a tubular heat exchangers, first we have to draw a very simple diagram, schematic diagram, in which what has been shown, there is a pipe in which a fluid is flowing, and the fluid is at high temperature, because as it is at high temperature, so that's why it has been denoted by H. Fluid H is coming in the pipe and leaving the system. Okay, so the fluid H coming and leaving the systems. Over this pipe, there is a provision of another pipe in which a cold fluid C is entering and it is leaving the systems at point 2. So in this diagram, there are 2 points, point 1 and point 2. At point 1, cold fluid is entering and hot fluid is also entering. Fine. And at point 2, the cold fluid will leave the system as well as hot fluid will leave the systems. So you can apply your common sense. Let the temperature is 80-90 degree here of this hot fluid. Okay, let assume it is 80 degrees centigrade, and the temperature of the liquid here, it was around 5 degrees centigrade. So as this liquid will move in this direction, so the temperature of the fluid C will increase, like C will increase as it will exit the system. Understand? Because it is gaining the heat from the hot fluid via this tubular pipe. Similarly, the temperature of fluid will decrease as it leaves the system. So the temperature of the H will decrease and temperature of C fluid will increase. Up to here, I think everything will be clear. So if you can recall our first unit, then when we were talking about the energy balance, if the system is working under steady state condition, then we can establish, or we can write a equation of energy balance for this system. We can say that the energy loosened by this hot fluid will be equal to energy gained by the cold fluids. Fine. And Q is equal to mc del T. We know Q is equal to mc del T. So here this m dot is indicating mass flow rate, H is for the hot fluid, Cp is the specific heat of that particular product, which is hot fluid which is flowing inside, H is for the hot, and Th is the temperature, Th inlet is the this temperature, and Th exit is the this temperatures. So this value is giving the amount of heat that has been dissipated, or this value is indicating this much amount of heat will be gained by the hot fluid, and it will equal to the amount of heat received by the cold fluid, and that can be given by mc cpc del tc exit, because here the temperature is high na? In this case we have taken inlet minus exit. In this case we will take exit minus inlet. Fine. So these two equations, or these two portion of the equations, are indicating that this is the energy loosened by the hot fluid and this is the energy gained by the liquid fluids. Fine. But this equation does not solve any problems. To solve these problems, we have to calculate the heat transfer that is taking place perpendicularly in any portion of the, at any portion of your tubular heat exchangers. So let this is the position 1, and if we consider a small part of this tube, so this material is flowing from this direction to this directions, but heat is transferring perpendicularly na, because the liquid fluid is flowing over the pipe. So this heat will transfer in the all directions, means throughout the pipe. So if we calculate this overall heat transfer coefficient here, then we can write dq is equal to UA del T, that we have learned from our past equations, that Q is equal to UI AI Ti minus T infinity. So in this case, what we have written? We have written dq UA, in place of A we have taken a small area, and for del T we have for this Ti minus T infinity we have taken a temperature difference. dq is the small heat transfer that is taking place. Now I'm coming, what is this del T actually? If we talk about the del T here, del T is the temperature difference of hot, means the temperature difference that exists in this zone only. Let the temperature of the cold fluid is 5 degree and the temperature of hot fluid is 80 degree. So del T value will be 75. Fine. And if we calculate del T here, then del T will be for sure lesser than this value, because here it is maximum, and as it is approaching to this side, this del T will decrease. I hope you understand. So del T is simply the temperature of hot fluid at any location and temperature of cold fluid at any location. So, and we are considering the location 1 and location 2. Anyway, so for these equations we can write dq is equal to mhcp dth. This dth is the th inlet minus th exit, and dq is equal to mcp del tc. Del this dtc is equal to tc exit minus tc inlet. Fine. From here, what we can find out? We can find out the value of dth and dtc. So if from these equations the value of this dt and capital H will equal to this minus dq divided by mhcph. We have done very little shuffling, nothing else, and we have taken it a negative sign because the heat is decreasing. That's why we have taken it a negative sign. So now I'm coming to this value. From here we have find out the value of dth. dth value is this and dtc value is this. Now we simply subtract this equation from this value. I will subtract the value of dtc from dth. dth minus dtc. It will equal to d common th minus tc. Fine. And it will equal to, like, if we will compare these two equations, you will get minus dq divided by 1 mhcph plus 1 cp 1 by m dot, or mass flow rate of the cold fluid into specific heat of the cold fluid. So from here we have find out the value of, we left with the this d dt h d d bracket th minus tc minus dq plus into bracket whatever the value has been shown. Now in the next step, what we will do, we will put the value of this dq from here, and this dq we know it is u del t dA. So when I'll write the value of dq here, it will equal to u as it is. In place of del t, I have written here th minus tc. So this th minus tc has been shifted on the left hand side, and it will be a part of denominator, or you can say, yeah, th minus tc will be on the bottom side, and this minus u del t has been shifted there, and a dA. Okay. So here you have to little focus. Simply what I have done, I have put the value of dq here, and as I put the value of dq here, this dth minus tc was there, so this dq was equal to u del t. So in place of del t, I have taken th minus tc, and it has been shifted on the left hand side. That's all. Rest of the things, u and dA has been multiplied with this value. In the next step, we will integrate it, and it is something like dx by x. If we integrate it from dx by x, then it is natural logarithm of x. So integrating the equations, and what will be the limit of integration? It will be from 1 to 2. Now here it is something to focus. Here it is 1 and here it is 2. So this is your TH minus TC. Na? So TH minus TC, TH is the TH inlet and TC inlet. In the next equation it will be covered. So if we will integrate it from position 1 to position 2, then at position 1 what exit? TH inlet exit and TC inlet exit. And at position 2, TH exit minus TC exit. At position 2, TH exit exist and TC exit exist. Understand? Rest of the thing will be same. This dA will be integrated from 0 to a, you can say. So it will be a. So minus UA 1 divided by rest of the thing will be same. So here the thing is that TH inlet minus TC inlet has been taken as del T1, and this TH exit minus TC exit has been taken as del T2, just to reduce the size of this ongoing derivations. So in place of this value we can write here del 2, and in place of this value we can write here del T1. So from here we find a relationship that natural logarithm of del T2 by del T1 is equal to minus mu a UA bracket 1 by MCP and plus 1 by MCP, whatever. Okay. So in the next step what we will do, we will put this value, we will use the first relationship, we will use this relationship MHCPH into TH inlet minus TH exit is equal to Q. Fine. So this is MHCPH. Na? So MHCPH, if we talk about MHCPH is equal to Q by TH inlet minus TH exit. So same story I have done here. I have put the value of this MHCPH here. So it will come to Q by this value TH inlet minus TH exit plus similarly for this it will be TC exit minus TC inlet divided by Q. Fine. In the next step what I'll do, this Q is common in both cases, so I'll bring out this Q out of the bracket here. Now what left here? TH inlet minus TH exit. Okay. Plus TC exit minus TC inlet. So this is something A minus B into bracket plus A minus B. So when you will open this bracket, whatever A minus B and C minus D you can write. So when you will open this bracket, TH inlet will be as it is here, and when you will open this bracket, then TC inlet will come here. So we will do little reshuffling. TC inlet we have shifted here minus TH exit minus TC exit. So we have changed this format TH inlet minus TH exit into TH inlet into TC inlet, and this is something equal to del T1 and del T2. So in place of this TH inlet and TC inlet we can write here del T1, and for this value we can write here del T2. Next step. So now we have a equation natural logarithm of del T2 by T1 is equal to UA upon Q, and in place of that inlet exit we have written here del T1 minus del T2, and now from here we can find out the value of Q, and Q will be equal to UA del T2 minus T1. Fine, because it was a negative sign, so this has been flipped now. If you will remove the negative sign, then the inside terms will be T2 minus T1 divided by natural logarithm of what you say T2 by T1. So this Q is equal to UA del Tm, and this del Tm, del TLM generally we used to write, and this del TLM is equal to T2 minus delta T2 minus delta T1 divided by natural logarithm of delta T2 by T1, and this is known as LMTD. This TLM is called as logarithmic mean temperature difference, and this equation is used to design a heat exchanger and determine its area and overall resistance to the heat transfer. Fine. So this is all about for the what to say, this design of tubular heat exchangers. If you have any query, you can ask me. Thank you very much. How to stop it?